Welcome, everyone. I'm so glad that you're here today. I'm Erin Gray, Grants Manager with NumFocus, and I've just really enjoyed seeing so many presentations so far. We have a great one coming up, and I'm so glad you're here. Everyone, please use the chat, pop your questions in, your introductions. I love seeing the exchange of ideas and strategies today. I just want to turn this over to our wonderful next speaker, Jonathan Shi. Some of you may know Jonathan. Jonathan's a software engineer on Snowflake's Snowpark Python team and is a maintainer of the Modin project. And Jonathan reports that he enjoys building systems that are usable and maintainable. I think that we can all echo that for sure. I'm going to go ahead and turn it over to you, Jonathan, and thank you so much for being here today to present for us.
Yeah, thank you, Erin. She pretty much said everything there is to say about me. I'm Jonathan. I'm a software engineer with Snowflake, and today I'm going to talk to you all about bridging interactive data science and big data with hybrid execution. First things first, a quick obligatory disclaimer. Everything I'm talking about in this presentation is part of an already released feature, but just in case I do make any forward-looking / speculative statements, they don't represent any commitments or roadmap on behalf of Snowflake. I'm just a software engineer. None of my statements hold that kind of weight. In any case, I guess I've already been introduced. I work on the Snowpark Python team. I'm also a maintainer for the Modin data frame project, where we work to provide a parallelized implementation of the pandas API. And I'll talk a bit more about what that means in the course of this presentation. So I'll cover the following aspects of hybrid execution. First, I'll talk about the background of Modin and Snowpark pandas, why we have hybrid execution in the first place. And then I'll talk about the architecture and the design decisions behind our hybrid execution system. I'll go through a couple code examples, and I'll go over a quick performance evaluation of our system. All right, background. What is Modin and what is Snowpark pandas? Well, let's start with Modin. Modin is an open source data frame library that is meant to be a drop-in replacement for pandas. What this means is it provides an API surface that is effectively identical to pandas, the key difference being that Modin supports distributed computation libraries, in particular Ray and Dask, as its primary computation backends, unlike pandas, which is inherently single-threaded, single-core. At the end of the day, the goal of the Modin project is to let you write the same code for interactive workloads where you're exploring your algorithms, trying to come up with a pipeline, and the batch pipelines that you're running in your daily workloads to analyze big amounts of data. And the key here is with Modin, the idea is you can do all this in the same familiar pandas API that most people know and love. There's no need to rewrite it in SQL or Spark, which are typically languages that are much harder for people to learn and much harder to hire for. As a quick code example, if you were to, in your normal pandas notebook, just write import pandas as PD, with Modin, scaling the pipeline is as simple as writing import modin.pandas as PD, writing pd.read CSV or whatever other data frame ingestion / creation methods you have, and you can run the exact same data frame manipulations as you would with vanilla native pandas. So the second part of the equation now is Snowpark pandas. Well, Snowpark is a family of clients and execution environments on top of Snowflake that let you interface with the Snowflake warehouse without having to use SQL. And with the power of Snowpark Python, which is a Spark-like data frame library that interfaces with Snowflake, we use Modin to translate the same familiar pandas API operations, except now it gets to run in the Snowflake warehouse. So if you have data inside Snowflake SQL tables, instead of having to use SQL or some other interface like Snowpark Python to use your data manipulations, you can once again just write pandas. The import has changed slightly because of some technical reasons. We have to add a second line of import, in this case, snowflake.snowpark.modin plugin. But once you've done this, you can use custom functions like this pd.read snowflake function to read a SQL table out of Snowflake. And once you've done that, once again, you can continue using pandas operations to manipulate your data, just as before. So with that out of the way, we've built this nice feature where you can use the Snowpark pandas API to interact with all your data in Snowflake. But then why do we want to have a hybrid execution? Well, there's a few reasons. First off, the way Snowpark pandas works is it takes the user sequence of pandas API calls and it gradually builds up a SQL query lazily based on the API calls that happen, unlike pandas or even traditional Modin, which executes every single API operation eagerly. But one thing we noticed is SQL tends to not be very good for a lot of interactive use cases. In particular, a lot of users have data that's very small or even medium sized, which native pandas execution tends to be much better at. In 2024, AWS Redshift released a very interesting analysis of a bunch of queries that were run on their system, and Jordan Tagani from DuckDB, or from MotherDuck, excuse me, wrote a blog post dissecting the raw data that AWS released. One very interesting insight from this report is 75% of queries scanned less than 1 GB of data. The moral of the story here is that this is a bunch of SQL workloads. And even if SQL workloads are scanning less than 1 GB of data, we can expect that pandas workloads users who are probably not working with the same scale of data, a lot of their use cases are probably also for small/medium-sized data. Even if they want to work with data that's resident in SQL tables, they don't necessarily need the full scaling capabilities that an engine like the Snowflake warehouse can provide. Another thing we noticed over the course of maintaining Snowpark pandas is in a lot of situations, we had APIs that we didn't support within Snowflake or within the Snowpark pandas translation to Snowflake, or that had poor performance when we used the Snowflake SQL engine with our translated queries. As a consequence, we provided an escape hatch for users to convert their Snowpark pandas/Modin data frames into native pandas and then run their API operations that way. And we found that a lot of users were doing this. So the key insight with hybrid execution is because databases are bad at certain data frame transformations, which I'll elaborate a bit more on later, a lot of users, since they use small or medium data, since they frequently convert to native pandas anyway, we figured that it would be better to offer them the option of having their data frame operations automatically switch between Snowflake SQL or to native pandas execution as is necessary based on the APIs and based on the data they're calling. Another problem with SQL is even if the operations aren't very pathological, sometimes the generated SQL can become very complicated just because of the nature of the invariance that pandas has compared to those in a SQL table. I'll show you an example of what I mean by this. Here's a very simple pandas data frame operation. We're initializing a data frame with a single column label X and a single row with the value 0. We're adding this data frame to itself, and this toPandas method is just materializing the SQL query that the Snowpark pandas query tree would be generating. The SQL we emit to the server looks like this. And I won't go through this in excruciating detail because it is kind of a lot. It even gets more complicated if your query is much more complicated or if your API calls in pandas are more complicated. But the gist of it is this. Pandas requires us to maintain a lot of metadata in order to ensure that users have the same experience between Snowpark pandas and their native pandas code. In particular, in pandas expects all data frames to have a row position. But in SQL tables, there's not really this concept. Unless you specify an order by clause in SQL, there's no inherent ordering to the data frame. But in pandas, users expect their data to generally be ordered, so we have to maintain an explicit row position column. In newer versions of Snowpark pandas, we've optimized away the row position column to make things more efficient, but in many cases, we still have to pay the cost of maintaining this metadata across SQL queries. You'll also notice that there's a lot of aliasing in the body of this SQL query. This is to avoid label collisions because users can name the columns of the data frame whatever they want. We have a bunch of internal data frame column names that we need to maintain as well. So the SQL query just becomes very bloated very quickly as a result of all this aliasing. So this query is generated even after we've implemented a bunch of optimizations. If you were to naively implement something like this, it might become a more complicated join statement, but we have code to recognize that this is, in this particular example, a join with the data frame itself because we're adding df to df. We can optimize away a lot of the SQL we would have otherwise omitted, but for even more complicated operations, in particular, two things that come to mind are transpose and matrix multiplication, you could conceivably write SQL queries that can perform these operations, but they're very hard for the SQL engine to process and sometimes outright just impossible to do in an efficient manner. So to summarize, there's really 4 reasons that we want to implement hybrid execution in the first place. First off, we think it's better to do small workloads with native pandas execution. This is in large part due to avoiding network overheads. No matter how optimized the Snowflake warehouse is to perform operations on small data, in the time it takes for a user to submit a SQL query from their local device to the Snowflake warehouse, and then for the Snowflake warehouse to return with the result of a computation, especially for very small operations, native in-memory pandas could already have completed the operation. This isn't a problem of Snowflake, it's just a problem of the speed of light being too slow. Second, we can do workloads in native pandas that SQL doesn't support well. The examples I gave earlier of transpose and matrix multiplication come to mind. We do support transpose in Snowpark pandas. The query is quite complicated. You have to do a pivot. We have to do some JSON serialization so we can infer the types of the output columns, and then we have to do an unpivot. It's very messy. And even though we do support it within SQL in Snowpark pandas, it's not particularly efficient. Matrix multiplication, we have tried to implement it in SQL in the past, but we just could not find an efficient way to do it. Snowflake does have a special data type that lets you do matrix multiplication more conveniently within SQL, but Snowflake Pandas does not yet support this feature. So I've been talking a lot about how native pandas can do better in all these different use cases, but the reality is that for many users, native pandas just isn't sufficient. That's why they turn to tools like Modin. That's why they turn to tools like Snowpark Pandas in the first place. So the key insight here is that when your data becomes sufficiently large and when it would run out of memory in pandas, that's when we should definitely be switching to Snowflake, or in theory, any other distributed backends, because these backends are scaled. The Snowflake warehouse is well designed to perform computations on data of this scope. And fourth and finally, this goes back to the core promise of Modin, and even to a degree the core promise of Snowflake, that you can scale your data operations without needing to learn any new tools or frameworks. Within Modin, within Snowpark Pandas, you can continue using the same Pandas API that you've always been using with very minimal extra configuration. Now let's go over a bit about the architecture decisions behind Snowpark Pandas and the hybrid execution engine. The first thing to decide is when to switch between the different backends between Snowflake and native Pandas execution. Fundamentally, at the end of the day, the goal is just to identify which particular backend is going to be the best suited to perform each Pandas API call operation. What this really comes down to is, I've kind of been alluding to this the whole time, but if your data is small, you probably want to use native execution, but if your data is large, you want to use Snowflake. Because in Snowpark Pandas, most of our users are starting from Snowflake SQL tables, we typically will start in Snowflake execution by default, and then switch to native execution if it would make sense if the data is sufficiently small. There are a few places where we explicitly make decisions to switch. The first thing is we declare a set of APIs that we know will usually be faster to execute in memory. For such situations, we move the data out of Snowflake to the user's client first, and then perform the computation. Examples of where this might happen is for literal initialization, where the data exists within the user's machine in the first place. For example, the dictionary initializer I showed earlier, or even just a native array. If we were to use Snowpark Pandas execution in those cases, we would generally produce an embedded value statement within the SQL code. But if we can keep that in memory instead of having to issue SQL, you should always do so. Another example is transpose. As I described earlier, transpose gets pretty complicated in SQL. For almost all scenarios, it makes much more sense to do the transpose in memory. So for those sorts of operations, we will always move the data and then perform the computation in native pandas. We will also only switch if our results are known to be small enough. In such cases, this is a different set of APIs. We will want to perform the computation within Snowflake first, and then move the result of this computation back to native pandas in memory. Examples of this include aggregations, where generally you're taking either a data frame with a lot of columns or a lot of rows, and then you're compressing it down to either a scalar or a data frame with very few rows or very few columns. In these cases, we know the result of the computation will always be pretty small. And if that happens, if we expect the user to continue to do manipulations on the result of that data, because we know the data will already be small, in that case, it makes sense to do the aggregation on Snowflake, which is well suited to munge all this big data into something reasonable as a result, and then take the result into the user's local memory and just operate on it directly there. We will also switch to native execution if we detect a read Snowflake reads a SQL table that is sufficiently small. We notice that for users that have data in SQL, even if it's in SQL already, If the data is small enough, then it often makes sense to move it back to the user's machine already to do execution, because the SQL we generate to manipulate it later on can become complicated very quickly. Finally, the last case where we have to switch is if we ever join data frames between two different backends. If you're merging a data frame on Snowflake with a data frame backed by native execution, then we need to switch one of the backends to the other in order to make sure we can either emit SQL or perform the join in memory. So how does the switching mechanism actually work? If you look at this diagram over here, this gives essentially a high-level overview of how Modin is structured relative to all the different computation engines that it supports. Modin is responsible for implementing the pandas API front-end interface. This is the segment of the API where users just perform data frame operations or group by operations or aggregations, all that sort of stuff. Modin will then pass essentially a compiled version of these API operations down to a query compiler specific to each query engine that we support. For example, we have the Snowflake Snowpark query compiler, which is responsible for translating the pandas API operations into SQL that's then run on Snowflake. We have the local query compiler, which is responsible for essentially translating pandas API calls transparently back into native pandas execution. And we have the Ray query compiler, which takes pandas API calls and submits them as operations to the Ray cluster. The query compiler is responsible for interfacing between the pandas API interface and each respective execution engine. So in order to determine whether we should switch between different computation backends, we essentially do this computation for every single candidate backend. We look at the cost of moving data between backends, and we look at the cost of computing the data on a particular target backend. We then compare this to the opportunity cost of not moving the data, of keeping it on the original backend and performing the computation in that same location. And at the end of the day, we just choose whichever backend minimizes the sum of this total cost. Our heuristics for performing this cost estimate is not particularly complicated. We essentially just estimate the size of the data frames that are part of the operation, and we use the number of rows, the number of columns in the input to determine how expensive it would be to perform an operation or to perform a data transfer. One thing that's worth noting is that for the Snowflake backend in particular, because we might not necessarily know the size of a data frame generated from a SQL query, because our queries are built lazily, we have to keep an estimate of the data size that we propagate throughout the system. So we generally do an eager count query when we read from a Snowflake table, and then as we perform different API operations, we propagate a value that we estimate the total row count of the resulting SQL query on throughout the system. Lastly, query compilers are each optimized to provide a decent transfer implementation between two different systems. There's a few different ways that you could conceivably implement, for example, a system that transfers data from Snowflake out into native pandas. And because we have the power to modify the Snowpark library and to modify the Snowpark query compiler, we are able to provide the most optimized implementation that reads data from a Snowpark data frame back into native pandas memory and vice versa. Here's a few examples of what auto switching looks like in practice. Everything with hybrid execution starts with these two lines of import, modin.pandas as PD to bring in Modin, and Snowflake Snowpark Modin plugin to initialize Snowpark pandas. This sets your default back into Snowflake, and if hybrid execution is off, everything will just run as transpiled Snowflake SQL. The first example is as follows. This is the very simple self-join addition I showed you all earlier, where we have an in-memory initialization from a dictionary literal. In this case, we recognize that it's an in-memory literal, so it makes sense to keep the operation in memory for whatever the user decides to do subsequently. So this will always stay in memory because of the literal initialization. Here's an example where we're transposing data. Even though this reads Snowflake, which is a custom Snowflake method in Snowpark pandas, this is ingesting from a SQL table in Snowflake. Because the subsequent operation is transpose, we will pull this operation into native pandas to do as long as the data is sufficiently small, because transposed in Snowflake is kind of inefficient to do. So this is one of those APIs where it makes more sense to just execute this in memory. The third example here is combining two SQL tables with in-memory data. We have our first table generated from read Snowflake from a SQL table, And we have our second generated from read CSV from a local CSV file. We do offer an implementation that will upload the CSV file to Snowflake once you read it, but in this case, we can assume it's small enough that we decide to stay in native execution for the CSV read. The operation we do to combine these two is a simple merge on a common column, and whether or not this merge operation occurs in SQL or whether it occurs in local memory depends on the data size. For example, if read Snowflake produces a very large SQL table, and if read CSV produces a very small CSV file, then it makes much more sense to upload the CSV file to Snowflake and perform the merge in SQL there. Conversely, if read Snowflake has a very small SQL table and read CSV is a very large SQL file, or CSV file, excuse me, then it might make more sense to download the data from the Snowflake table back into memory so we avoid paying the upload penalty cost of uploading the CSV file to Snowflake. Finally, I'll go over some performance evaluation of some short examples of the hybrid execution system. This first graph over here compares performance of native pandas to hybrid execution to Snowpark pandas for the read CSV API of data frames CSV files of varying sizes. Note here that the y-axis is log scaled. The red bar represents Snowflake, blue for hybrid execution, and orange for native pandas. And you'll note here that pretty much across all data sizes, Snowpark pandas does not perform particularly well. This is kind of just inherently because of the fact we have to pay network overhead to upload a CSV file, whereas if we're producing a data frame in native pandas execution, that data just stays from the file system into the user's local machine's memory. There's much less movement involved. The key insight here is even though for the leftmost graph, the 10 by 10 bar, it looks a lot worse for hybrid execution than for native pandas execution, it's actually not that bad because the y-axis is log scaled. So this just demonstrates that the overhead for hybrid execution is pretty minimal compared to native pandas. And for the 1 million by 2000 row case, or 1 million row, 2000 column case on the far right of this graph, Snowpark pandas just can't complete in a reasonable amount of time because of how long it takes to upload the CSV file. So with native pandas execution, if people want to do manipulations on a data frame before saving it back to Snowflake or doing whatever else, it just makes more sense to keep it within native pandas execution, which the hybrid system chooses to do so here. The second example is benchmarks for the transpose API. As I mentioned earlier, this is a very adversarial operation for SQL because of the schema being hard to know in advance when you do a transpose, and because the query just becomes very complicated. So you'll notice the absence of a red bar for any graph with 2000 columns or 1 million rows. This just means that Snowpark pandas, when we tested it, just did not complete the operation, again, in a reasonable amount of time. On the other hand, hybrid pandas and native pandas are perfectly capable of doing transpose. You'll also notice the absence of hybrid for the 1 million row situations. In this case, because our data frame originated in Snowflake in a SQL table, the decision engine behind hybrid execution recognized that 1 million rows is a lot, and it decided that we did not want to pay the transfer cost of moving 1 million rows out of Snowflake back into the user's local machine. We set the threshold at which to transfer the number of rows at which we transfer data out of Snowflake to be 100,000 by default, because that's typical for what we observe to be the breakpoint between Snowflake being better than native execution. And in this case, we didn't want to mess with our general case default tuning. So we decided that if you have 1 million rows, you'll stay in Snowflake execution. And in this case, it just happens to mean that transpose won't terminate. The last example API here is dot products, multiplying two matrices. And in this case, we just don't implement this in Snowpark pandas because it's not efficient in SQL in the slightest. And at the end of the day, hybrid execution in native pandas times out at 1 million rows, but at the very least, it is capable of doing the operation for smaller data set sizes. So if users want to do dot products on their data within Snowflake tables, hybrid execution will let them do it automatically without having to make any code changes. The last thing I want to show you is this sample workload benchmark that we adapted from a customer notebook. This is a pretty typical pandas workload. There's a bunch of joins, there's a bunch of filters, and there's some group by aggregations in the pipeline. And you can see the performance characteristics across the different engines here in this graph. With Snowflake in Snowpark pandas, The engine performance doesn't particularly care about the number of rows in the input data. You can see the line is pretty flat. On the other hand, native pandas looks pretty parabolic. It starts out very fast for very small data, but as the number of rows grows in around the 70,000 range, it starts to become slower than Snowflake, and it does not really scale at all. With hybrid execution, you essentially get the best of both worlds. If your data is small when you're doing your exploration, you get to use native pandas, you get to stay very fast. Once your data is sufficiently large, it will start to follow the scaling profile of Snowflake because it sends all your queries to Snowflake instead, where it's much more optimized to handle big data operations. You'll notice that hybrid does not perfectly track the best performance option. This is kind of what I alluded to earlier, where we have a 100,000 row threshold by default for when we switch between execution engines. And again, we decided not to test to the benchmark too much and just leave it at what we felt to be a reasonable row threshold across all the workloads we examined. All right, and that's all I have. Thank you all for coming. I guess I'll leave the last few minutes for any questions that come up.
Thank you so much for that presentation, Jonathan. I don't see any questions yet, but I'll give everybody just a moment to drop any in there in the comments or in the Q&A. Otherwise, we will end. We do have the Discord channel. If you think of any questions later on and want to reach out to Jonathan, you can jump on the Discord channel and ask any questions there. But it doesn't look like we have any right now. So, Jonathan, thank you so much for your time today. We really appreciate you. And everybody enjoy the rest of the conference. Thank you.
Yeah, thank you for having me.